It probably doesn't surprise you to learn that I drink a lot of tea. Hot, iced, black, herbal, green, you name it, I probably drink it. But ever since I moved to the US 10 years ago, there's one thing that's really bugged me about the tea making process, and that is, yes, American kettles. Now, are they fine? Yeah, they work. They work absolutely fine. But the problem is I've experienced better kettles. I've lived in Europe. The power there is much higher voltage. Things work in twice the time. And so while I live with the kettle, I'm kind of on an endless quest to figure out what is the best way to boil water. And well, I think we'll go through some tests. The humble electric kettle here will be our baseline, but there's a number of things that I really want to try just for my own edification, if nothing else, and also should be pretty interesting. And when I say the best way to boil water, I mean best is subjective, right? Is it fastest? Is it most efficient? Is it most fun? Is it safest? I don't really know. I kind of will know it when I see it, if you know what I mean. But in this case, I'm probably looking at some combination of efficiency and speed. And given that my main bugbear with the American electric kettle is in fact speed, speed is probably the main thing I'm focusing on here. So let's look at what the performance is of this normal electric kettle before we begin. Now, I should obviously point out that most American households don't have one of these. They in fact just go and boil their water on the stovetop or the hob, or occasionally they will just use a microwave. Although honestly, most of the time it's using coffee makers and similar devices that boil water in the process. Either way, this is a standard US electric kettle that I got from probably Target or something like that 5+ years ago. It lives here in the workshop. It performs admirably well, but let's see how it does. Now, I'm going to try and aim for a consistent amount of water on all of these tests. And so I'm going to start with half a litre, 500 millilitres. And we're going to put that in, and of course, we're going to measure the initial temperature because if the water is warmer at the beginning, it will take a little less energy to warm it up and comparisons won't be as fair. Either way, water goes into the kettle, and then of course the requisite blue LEDs, the legally required part of any modern technology, come on. And then finally we can get boiling. Now, in actuality, when you only put half a litre of water into even an American electric kettle, things do get going pretty quickly. You can see here that the bubbles start to form and you see pretty obvious starts of boiling, and then eventually we get to what I call a full rolling boil. And it wasn't too bad, taking 2 minutes and 41 seconds, and on my attached power meter, we can see that it's used 55 watt-hours of energy. And of course, if we measure the temperature of the final boiling water, we'll see that it's the expected 95 Celsius or 203 Fahrenheit. Wait, hold on a second. Now, I'm pretty sure I remember the boiling point of water in Celsius specifically being 100 degrees, and it is at sea level. The problem here is I'm at altitude. Denver is famously 1 mile high, and as a result, there is 1 mile less atmosphere above me, pushing down and making everything have higher air pressure. Lower air pressure means that it is easier to boil water, and so water at Denver at least boils at pretty much exactly 95 degrees Celsius. Can I change that easily? Not without making the entire workshop a pressure vessel or somehow shipping all of this down to, like, I don't know, San Francisco, and I'm not going to do that, despite how good that city is for food. So instead, we're going to run all these tests with boiling here, meaning boiling at 95 degrees Celsius, because honestly, that's the thing I have. I can't really change it, and it's still a pretty good comparative test anyway. But of course, this does beg the question. If you can boil water at a lower temperature with lower air pressure, can you in fact boil water at room temperature? Well, it turns out, yes, you can. And let's just go prove that because it's fun. This is a vacuum chamber. And it's not a particularly exciting or large vacuum chamber, but it will do the job in this case. It's a big steel vessel with a rubber mat at the bottom and then a big old glass lid, which obviously has to contain the implosion pressure. Now, it's not particularly difficult to do this, but I thought I'd demonstrate it anyway. And so again, I got a small amount of water and placed it inside the vacuum chamber, along with a GoPro, so you can see the action from inside, because once you start taking the air out, the top tends to steam up. So everything's ready. The vacuum pump is attached. It's not an amazing vacuum pump, but in this case, it'll do the job. And I take a quick recording of the ambient air pressure in the room, which is, again, lower than sea level. It is 840 hectopascals. So vacuum pump on, and pretty quickly, in fact, you can start to see evidence of boiling. The sort of small bubbles start to form inside the water, and then in honestly a surprisingly short amount of time, it develops into a more of a boil and then pretty much what I call a full boil. Now, this does take the vacuum pump 3 full minutes to bring the air pressure down to a point where it boils. And in fact, if we look at the air pressure, differential at least, the gauge obviously reads the difference in pressure between inside and outside, not the absolute pressure. The gauge reads minus 840 hectopascals. Now, it's not a super high quality gauge and vacuum chamber, but that basically means it's effectively at 0 absolute air pressure. And so we've got close to a total vacuum. We're not doing actual science levels of total vacuum here. And even though it took 3 minutes, it only took 9 watt-hours of energy to take all of that air out. So in terms of power versus the 55 watt-hours that the kettle takes, it's way more efficient, but of course, while it's boiling, it's not actually hot. If you take off the lid straight after you let the air back in, you can feel the humidity and moisture in here. It feels a little bit warm due to the humidity, in fact, but it's not hotter, it's just at room temperature. It just happens that water boils at room temperature at 0 air pressure, essentially. Funnily enough, though, the GoPro, which was in here, did get very warm, as it turns out that GoPros really don't like running in a vacuum. They'll do it, but obviously taking away one of their main ways of getting rid of heat, yeah, not great. So the GoPro was honestly close to boiling point itself, even though the water wasn't. That long digression about boiling points aside, let's get back to the electric kettle here. Now, it's probably useful to work out the efficiency of the kettle, and we can do that. Remember, there was a power meter plugged into it, and I took the initial and final temperatures. If we do a little bit of maths, we can work out that it should take 161 kilojoules of energy to raise half a litre of water from 20 to 95 degrees Celsius. And as we measured it, it was 55 watt-hours, and 55 watt-hours is equal to 198 kilojoules. So in fact, if we look at it, it's basically 81% efficient. Now, I don't know about you, but that's actually pretty good. I'm not surprised. Electric kettles are famously quite efficient devices. The most efficient thing you can do with electricity basically is to turn it into entirely resistive heat. And the base of this thing is just basically one massive heating element. The losses are going to be like a little bit of loss not conducting to the water, and of course some loss from this glass surround here, but you know, I can't really ask too much more in terms of efficiency. Or can I? This is a more efficient device, at least in theory. It is also an electric kettle, but crucially, it is in an insulated container. If you look inside, you can see it's basically one of those insulated drinks containers, but this one happens to have the bottom portion be an electrical heating element with a power inlet where you stuff a power cable. Funnily enough, this is the thing I bought to use in my camper van, under the belief it was more efficient. I have never actually tested that, so let's test it. Now, while the Jettle does not have the legally required blue LEDs, it does have the other scourge of modern technology, capacitive buttons. However, I'll kind of let it off as it has a nice little temperature readout at the bottom that tells you how hot it is, and that's actually really useful. Anyway, I get this thing underway and, well, it starts boiling. We can't see it, obviously, it's in this opaque container, but I can kind of hear it in the background as I'm running this experiment, and it takes a while. In fact, if you look at the power draw of the Jettle only draws 370 watts, versus the 1,370 watts that the bigger kettle does. And so maybe it's more efficient, but it certainly is slower because it's pumping a lot less energy into that water as it goes. Either way, it does make steady progress. The temperature display on the bottom slowly ticks up, and then at 6 minutes and 37 seconds into the experiment, finally it reaches boiling point. And fortunately, the Jettle actually kind of understands being altitude and cuts itself off when it feels it's not getting enough progress in temperature rise. And so it genuinely does actually start boiling at 95, unlike some of the other devices here, as we'll see. Now, I can only fit 400 milliliters of water into the Jettle. It's just not a full half liter big inside, but I corrected my calculations for that and the energy expended. It turns out that the Jettle takes 39 watt hours to boil 400 milliliters of water, which if you do the requisite maths is 90% efficient. So indeed, having that insulated outside gives it a 10% efficiency gain over this glass-walled blue LED thing over here. So that's pretty good. And honestly, one of the reasons I like the Jettle for the camper van is it's actually very compact, and that lower power draw is kind of useful in a place where, yes, the camper van can take 1.5 kilowatts of power in its wiring, but sometimes it's nice just to have it run a little bit lower, a little bit slower, and have that kind of spill resistance in case you tip it over. But so far, we've just talked about electricity. And of course, there are many, many other ways to boil water. In fact, the very first way of boiling water that I think humanity discovered is fire. And so let us go from the realm of electricity to the realm of fire. Or more specifically, the power of burning isobutane into a complex metal heatsink, just like our ancestors did. This is a jet boil. Probably familiar to many of you who are campers or hikers or backpackers. It's kind of the standard for portable camping stoves these days. Now, there's a few notable features of the jet boil, but the main one is, of course, the aforementioned heatsink here at the bottom. It pairs with the burner to have a very efficient use of the heat pointed at it. Your average stovetop or hob at home with a gas flame is just wasting loads of heat around the sides of the pot. This captures that heat in here as it goes through the fins of the heatsink, and so it's significantly more efficient. I'm not even gonna bother testing boiling water in a saucepan. That's just gonna be worse than this is. And so, I generally use these as well in the field. And it's probably best to know, like, hey, is this actually more efficient, especially inside a camper van case, than using electricity? The other nice part about using a portable stove rather than the one that's piped into mains gas is that I can actually measure the amount of fuel used by weighing the canister. I have a scale sensitive enough to do fractions of grams, and so I can weigh this down to the 100th of a gram before and after I run the experiment to see how much fuel I used, and again, get a good efficiency value. As always, the test is on 500 milliliters of water, and honestly, as soon as I light this thing on, you can hear it roaring. The jet boil's name is no joke. It absolutely lives up to its claim. And even with what is a pretty large amount of water for its relatively modest size, it very quickly starts boiling, and it reaches a full boil in 1 minute and 40 seconds. Now that's quick. It is a lot faster than our humble electric kettle here. But of course, how efficient was it? Looking at the jet boil, there is a little bit of padded insulation around the outside here, so that will help. But of course, we're comparing electricity to burning gas, and so it's going to be a little bit different. Weighing the canister, I find that I used 4.7 grams of butane, which is equivalent to 230 kilojoules. Now, based on my temperature measurements of the water when I put it into this one, it should have taken 151 kilojoules of energy to boil this water, and so we can conclude that the jet boil is 66% efficient. At first glance, you may say, hey, that's way worse than the electric kettle. And it is if you do that basic calculation, but you're forgetting something. This is going directly from fuel. The power for this kettle has to come from somewhere. Now, if it's being powered entirely off solar panels, that's great. Then this obviously is way more efficient. That power is not using a non-renewable resource. But here in Colorado, our electricity power mix is about 2/3 fossil fuels and about 1/3 renewables. So in fact, somewhere further down the transmission grid, this is also burning fuel in a giant power station. And trust me, that power station is not 100% efficient at turning fuel into energy. And so while this may seem worse up front, combining this with its transmission and generation losses may mean they're actually probably reasonably similar in terms of their overall efficiency performance from a fossil fuel. But of course, fuel is so last century. We can harness the power of stellar fusion, specifically the stellar fusion occurring in our closest star, the Sun. That's right, we can use solar panels. Now, as I mentioned, you can run either of these off of solar panels. That works perfectly fine. My van, which is literally just to the side of the frame as I record this, has 400 watts of solar power on its roof, which means that we can work out what it would take on a bright sunny day to collect enough power to power both of these. Now, we can actually look at the jet boil as an example. The van has an alleged 400 watts of power on the roof. I get between 360 and 400 based on how sunny it is and how high I am. Again, altitude actually gives you better performance than solar panels. Less atmosphere means the sunlight is dimmed less. But either way, it's pretty close to the 370 watts that this uses. And so in fact, as long as the sun is out, my van collects exactly as much power as is needed to run this continuously, which means that 6 minutes of sunlight on those solar panels, well, that's enough to boil 500 milliliters of water. But I feel like that's cheating. Solar panels, they're normal, everyone understands them. You can just go buy like a 100 watt unfoldable solar panel from a shop and then do the math and be like, well, if 400 watts takes 6 minutes, 100 watts will be like, I don't know, 25 minutes or something like that. It's just too easy. I wanted to see if there were some more interesting ways of harnessing the sun more directly. And so I turned to everyone's favorite hive of very odd ideas, the internet, and looked up a couple of ideas for directly boiling water from sunlight. And this was the first thing I found that piqued my interest. It's from a brand that is, I'm going to say, too prepper-y for my taste, but it is described as a sun kettle. And the idea is that it has a insulated interior, a bit like the Jettle or another vacuum-sealed chamber, but it also has these solar mirrors that kind of unfold. And the idea is that you unfold the mirrors, you latch it all into place here, and then you point it at the sun using the little stand. Now, it's kind of ridiculous. I did not have high expectations, and the box advertises many things on it, including the fact that it is advanced, convenient, and also stealthy. But at no point does it say that it's fast. And so I thought I should give it a go and see how it does. I had this outside on admittedly a winter's day, but a very classic Colorado winter's day where the sun is incredibly bright and at basically full strength. And I placed it outside, poured 400 milliliters into it. It does not hold a full half liter, roughly around noon. Unfolded and angled directly at the sun, even propping up a little bit to get the angle perfect given it's winter and the sun is lower here. And, well, I waited. I waited 10 minutes and came back and checked the temperature, and it had gone up 8 degrees Celsius. I waited 40 minutes, coming back every so often and checking it. And even after 40 minutes, it had got to a 48-degree rise. And so I went away, I had some lunch, I watched some television, all the while checking every 10 or 15 minutes or so. And then finally, after 1 hour and 50 minutes, I came back to finally find boiling water inside of it. Now, I'll admit, the box tries to set expectations about how slow it is, but even this chart on the box lies. It does not take up to an hour. It takes almost 2 hours to boil a mere 400 milliliters of water inside this thing. Barely enough for a single good cup of tea. Now, is it stealthy? I guess it's stealthy if that's what you want in your water boiling technology. Honestly, really does not meet any of the criteria for best in any other fashion. And also, all that glass and stuff in here seems pretty fragile. So, rather unsatisfied with the sun kettle, I turned to the internet again and thought, well, what else can I find? And that's when I found what was described as a solar cooker. The reviews for the solar cooker included things like the phrase, almost too powerful. And so, of course, I could not resist buying this thing, even though it was some weird shipping and didn't turn up for a week. But when it did turn up, I got a box of bits. And as with many things I buy on the internet, a much larger box of bits than I was necessarily expecting. The total diameter of the thing is 1.5 meters. It is not absolutely gargantuan, but it's pretty large for a single person to lug around, and it certainly isn't stealthy in any sense of the word. When I wheeled it out the back of the workshop here to test it, at least 2 of the neighboring units had people come out and look at it confusedly and wondered what I was doing. So it will definitely attract attention when you've got a giant parabola pointed at the sun. But here's the good thing, it's really powerful. I started out placing a small cup of water just to test it in front of essentially the focal point of the mirror. And it's so hot there that as soon as I got the cup in the beam, the paint, the matte black paint on the outside of the cup, which was applied at the factory, presumably a powder coat or something, started bubbling and flaking off. And I could hear the spot where the sun was touching the metal, that water was flash boiling, and you could hear bubbling immediately as you placed it in the beam. So very good sign there. I thought, all right, let's do the proper experiment. So I went and got a kettle, which was a relatively dark gray. I thought it was pretty absorbent. Placed again, 1/2 liter of water into the kettle, rigged up a reasonable system to hold it at the focal point rather than me sort of dangling it around with long tongs, and then pivot it into the beam. And again, within seconds, you can start hearing flash boiling of what's going on in there. Now, of course, that's not the whole water. It's only a small part of it, but like, it sounds intense. And of course, it's quite hard for me to measure the temperature of this thing because I can't get my hand near the focal point because the temperature there is so strong. Like, it's not even sunburn. Your hand would start getting really badly hurt if you place it in that beam. Wanting to try and find a non-contact temperature measuring solution, I did go and get my thermal camera, and that registered the temperature at the focal point at around 150 degrees Celsius or around 300 degrees Fahrenheit, which is, I don't need to tell you, pretty warm. And of course, this thing boiled quickly. Not as quickly as some of the other things, the jet boil here still definitely wins, but in 3 minutes, it reached a pretty good rolling boil, and I had to pivot it away because the steam was emitting from the kettle at a pretty rapid rate. That basically means it is as quick as a US electric kettle, and of course, efficiency-wise, it's perfectly efficient as long as it's daytime and there's not too many clouds in the way, which fortunately in Colorado is not a huge problem, at least the clouds part. But it certainly isn't very convenient. This thing rolls around on wheels. You have to like manually crank it to adjust the azimuth angle so it perfectly matches where the sun is. And trying to get something suspended at the focal point without having yourself burned or your retina scorched. You have to wear sunglasses the whole time, by the way, because the thing's so bright. It's just a lot to deal with. And so while it's pretty quick, it's a good baseline, it's really not very convenient and honestly kind of dangerous. So we looked at a few things, and honestly, we've kind of seen that the direct solar stuff, it kind of works, but is very inconvenient for one reason or the other. The jet boil does pretty well, but obviously you've got to then cart these canisters around everywhere, and that's kind of annoying. And our electric kettles here, well, this one's even slower than this one, despite the fact that it's more efficient. And of course, the key problem here is that the electric kettles are limited by voltage. The US standard voltage is 110 or 115 volts, whereas in Europe it's 230, it's double. And the amount of power that you can get down a wire into the kettle is basically limited by that voltage. A standard wall socket here in America only gives out 15 amps, 20 if you're lucky. And the code for electrical devices like this is they can't draw more than, I think, 1400 watts at any given time. And so how do we overcome those limitations? Well, we can increase the voltage. There's 2 parts of this, of course. The first part is having a kettle that is designed for that higher voltage. Well, look at that. Here's another kettle. And crucially, this one has a different plug on the end. In fact, it has what I would argue is the best plug in the world, which is a topic for a different video, the UK plug. Now, the many advantages of this plug aside, this means that it accepts 230 volts at a full 13 amps, which means you can pump an absolute ton of power into this thing in one go. But here's the problem. I don't have any sockets like this in the workshop because all the sockets I have in here are 115 volts. Well, that's not quite true. I have one socket in the workshop that is three-phase power. Now, the intricacies of three-phase power are too complex to go to, except in their own separate video. YouTube has many of those, I imagine. And so I'll summarize it. There are three phases in the workshop. Each phase is offset from the other by 120 degrees. It's how the waves overlap. But the point is, each of those phases is 115 volts to neutral. But if you bridge two of those phases, you get a theoretical 208 volts because they're offset enough that the peaks and the troughs line up in a certain way. And three-phase power is pretty common in Europe as well, but there, of course, you have 230 volts often on the individual phases, and bridging them gives you a 400-ish number, much higher than you would otherwise get. But what that means is here in the workshop, I could get, if I wanted to, 200 and something volts out of my special three-phase socket. Annoyingly, that three-phase socket is behind the laser cutter, and it's kind of a pain to dig it out. But there's something else. American houses, unlike many European houses, are also multi-phase. Now, everyone thinks American houses are actually 115 volts, but they're not. The feed to American houses is two-phase. Each phase 180 degrees, entirely opposite the other one. And each phase is 115 to neutral. But if you tap into both phases, you get 230 volts phase to phase. And this, in fact, is how, here in the US, things like electric tumble dryers and electric ovens actually work. They are plugged into both phases. They have 230 volts. Because even despite the overall American system, they were like, well, some things are going to need the actual good voltage, and so those ones actually have good voltage. But again, these are special sockets often hidden behind the oven and the oven cavity or behind the tumble dryer. I don't have to go and pull my tumble dryer out every single time I want to make some tea. But remember, there are two phases going into a house, and there are three phases going into this building. Now, you don't want to unbalance the phases, which means that you don't want to put all the different electrical sockets on a single phase. And so in fact, sockets are generally spread across the two phases in a house or the three phases in a commercial building like this. And depending on which socket you plug into, you get a different phase. Now, some of you have probably figured out where this is going. And I do want to remind you, do not do this at home. But if you think about it, you have access to two phases just through normal electrical sockets, because you can take two sockets that are pretty physically close, but on different phases, take their live pins and feed each of the live pins, one into the live of this plug and one into its neutral. And then this plug will see 230 volts. And how do you do that? Well, you make a death cable. There are several different versions of a death cable in American wiring. The most common one is the male-to-male extension plug. You often see people who've wired their mains voltage Christmas lights in the wrong way around their tree, kind of try and go by. But this is a different kind. It is two normal extension cords with normal American plugs at the end, brought together into a UK socket. Now, weirdly, while I could buy the two extension cords from my local hardware store, they didn't have UK sockets in stock. Strange. So I ordered that off the internet. But the result is honestly terrifying. Two extension cords with normal American plugs on the end, long enough that you can go and find two different sockets on two different phases, combined into a UK socket. Now, ignore the questionable entry of one of the cables in the back. There wasn't enough room here. But essentially, the neutrals of both of these are discarded. They're capped off with insulation. And then the live of each of the different sides is brought to a different pin. One goes to the actual live pin in the UK socket, and the other live goes to the neutral pin, which of course still works because AC power is very strange. The end result of this is a cable that you can plug into 2 different phases in your house, and that will give you 230 volts at the socket. So let's test it. This video is genuinely the first time I tried this cable, and for safety reasons, I did actually try it here in the workshop. Now, as I mentioned earlier, the workshop only gives you a theoretical 208 volts between phases, not 230, but I figured that's close enough. And crucially, all of the electrical wiring here is in very obvious wall-mounted metal conduit. The risk of electrical fire here is much smaller. If it does happen, it's easily accessible with the correct fire extinguishers. And so with that, I plugged it into the 2 different phases. I defeated the obviously superior safety mechanisms of the UK socket, and then measured the voltage and got a surprisingly decent 215 volts of difference. I presume that the phases here are just slightly out of sync with each other, or maybe they're running a little bit higher than normal. Either way, well within normal tolerances for what they're supposed to do, and even better for my purposes, 215 is getting appreciably close to 230. Once again, I pour 500 milliliters of water into the kettle, and it's a perfectly normal kettle at this point, just from a different country. Plug it in and slightly reticently turn it on. And lo and behold, it just operates as normal. You wouldn't know it was thousands of miles away from home on a somewhat hacked together electrical circuit, and the thing merrily starts boiling pretty rapidly. And this is where you can see in person, especially, the sheer difference between the American and the European kettle. You can see the evidence of the boil happen almost immediately. The noise happens very quickly, and it reaches a rolling boil very rapidly. In fact, it reaches it in exactly 90 seconds. That is basically twice as fast as the American kettle. And hey, we doubled the voltage, so that's a pretty nice relationship between voltage and speed there. And in terms of efficiency, well, I had it plugged into a power meter. That power meter was only on a single leg of the extension cord. It's a US meter, so it has to go on one of the ends. And so it's only measuring one of the 2 phases. However, that basically means, and don't get angry at me everyone out there, we can effectively double its reading to get the power from both phases, because we're saying it's effectively double the power. It's not exactly, but it's close enough for this experiment. Either way, if we take the power meter reading and double it, we get 52 watt hours. And 52 watt hours for the European kettle is basically the same as the 55 watt hours for the American kettle. And I'll bet you the extra 3 are either a measurement difference, or it's the fact that you just lose more heat as you boil more slowly, or something like that. Either way, you can see that the efficiency of both of these kettles is the same. They use basically the same power to boil the same amount of water. However, this one boils twice as fast, and boy, isn't that better. Is it actually better though? Like, it's faster, sure, and it's as efficient, but we are overlooking the fact that if I was to put this in my kitchen, I'm gonna have to have this contraption, this death trap, spread across 2 different sets of outlets. And I've tested either side of my cooker in my kitchen, they're different phases. I could totally bridge them, except for, of course, the other fact that my house has ground fault interrupters on its circuit breakers. And so if I start taking power out of one side and not dumping it back into the neutral, it's gonna trip, it's gonna be unhappy, and I think also just wouldn't work. So while yes, I can use a UK kettle to boil stuff faster, maybe I'll even leave it hooked up here in the workshop for a bit, because again, the fire risk here is much more addressable. I still don't feel great about putting 3 kilowatts of power through some not terribly made, but still like amateur grade wiring here. And in general, like, I'm usually okay waiting an extra 90 seconds to get to the normal US kettle situation. Looking at all the things I've tested, what is the best way to boil water? How should I be making tea? Well, I've been burying the lead here. None of these are what I use to make tea at home. In fact, what I use to make tea at home is this Japanese water boiler. The core of this Japanese water boiler is the same as the Jettle or electric kettles. It is an 800 watt electric heating element. But the key part of its design is that that is encased in a large insulating container, and then also it keeps it hot. you leave it plugged into the wall and it sits there and keeps it warm all day. And when you want hot water, you come along, you press the dispense button, and you just get hot water out. And that means that the effective speed of it is 0 seconds. And it turns out, as I said at the beginning, speed is what I value the most. It does lose out a bit in the efficiency department. As you can imagine, it is keeping the water warm, and even with an insulating surround around it, that's still taking more energy than boiling the water and letting it just pour immediately. In fact, I stuck the same power meter on it and measured how much power it took to keep a full 4 liters of water, its maximum capacity, warm for a full day. And it uses 400 watt hours of energy for a single day to keep the water warm. Now, that is quite a lot. Remember, one boil of half a litre takes around 55 watt hours. And so it's about 8 times as much power to keep 8 times as much water warm during the day. But it's a small price of convenience, and it's not a huge difference. If you're drinking like 4, 5, 6 cups a day, you're probably not boiling exactly the amount of water you need to make a cup. In fact, one of the most common things people will do with kettles is fill them up to like as far as they go and then just boil them and pour 1 cup of tea and then just leave them to cool down again. So it's my opinion the Japanese water boiler is actually about as efficient because you're not just overfilling the kettle and letting it cool down and just wasting all the power that way and letting all the other heat go to the house in the form of entropy. There is one other annoying part of the Japanese water boiler. It has a couple of different temperatures it can keep the water at, so you can have it either super hot close to boiling or a little bit lower. But as I mentioned, the boiling point here in Colorado is 95 Celsius, and the options on this machine are only 98 Celsius or 91 Celsius. And trust me, if you leave it on 98 Celsius, it will just sit there and the water will continuously boil inside it. And what you've basically got is the world's most over-engineered humidifier that just sits there emitting steam continuously until the thing drains in about, I think, 6 hours when I tested it. And so in the end, 91 degrees Celsius water is more than enough for the herbal teas that I make. Crucially, am I happy? Yes, I think it's fantastic. I have found a solution that is not terribly inefficient. It is very, very quick, an effective time of 0, and I use it pretty much every day. But of course, well, there are other options. I will say that I use the Jetboil whenever I go camping. They're really good. As you saw from the experiment, they're really quick. And this is sort of the bigger, slower one. Like, I've seen these genuinely boil water in under 60 seconds. It is absolutely ridiculous what they can do. If you are camping or out and about, I highly recommend one. And honestly, just as a backup mechanism for having to heat water in case of power outage or similar, they're pretty good. Just as always, remember, you shouldn't burn fuels inside without adequate ventilation. That's how you get carbon monoxide poisoning. Please be careful. And here at the workshop, I don't have a second Japanese water boiler. Well, not yet. And so the trusty kettle here does the job. It's perfectly fine. Maybe I'll upgrade to the UK kettle. Maybe I'll have some permanent wiring going on. Maybe I'll fish out the 3-phase socket from behind the laser cutter and put an actual 3-phase plug on this so it can work without the risk of very worrying electrical fire. In the end though, I feel like I've learned a lot about the different things that I have used over the years. I feel really good about some of the things I do currently use. The Jettle genuinely is more efficient and is totally worth, I think, its compact form factor and the way it works. We'll ignore this thing. Never going to use this again, probably. And crucially, I now have a giant solar death ray that I've got to go and figure out what to do with. I'm going to go figure that one out, and I'll see you next time.